Assalamu alaikum, Chairman. I have the pleasure to present our study entitled The Numerical Analysis of a Laminar Transit Flow of a Pseudo-Plastic Fluid. We are team of modeling and simulation of mechanical and energetic Mohammed University in Morocco, and also nanostructures and advanced materials mechanics and thermofluid laboratory, Casablanca University in Morocco, and a second international conference on applied thermofluids and computational fluids mechanics. So I start with introduction, the plan of this presentation. I start with introduction, then problematic. Uh, After I present numerical method using here, then application and results, and finally I conclude. So the water hammer phenomena means a pressure surge or shock wave that can oscillate in a pipe system with a speed close to that of sound. So this phenomenon of non-Newtonian fluid flow are mainly found in natural and artificial systems, such as hydraulic circuits, cardiovascular circuits, air conditioning, circuits of gas routing for domestic or industrial use. But this progress pressure wave in the system can cause the pipeline to explode or implode. So now we move to problematic. So in this study, we consider pipeline with valve and reservoirs. So in this study also, we consider some assumptions and simplifications, such as quasi two-dimensional system. That means quasi indicate that Vt times Vr equals 0, and Vz the only velocity component that varies along radial and axial directions, and also the convective terms are neglected. So the governing equation, both global uh, and uh, and local, are presented here with different parameters such as average velocity, pressure head averaged, with speed, density, time, steady friction, uh, actual velocity, and also shear stress. So the particularity of this problem or of this study is to consider the both systems, local and global system. So here we move to non-Newtonian fluid equations because we consider non-Newtonian fluid. So this is the equation that presents, and also with parameters, apparent viscosity and shear rate. So, and the power law is used here to present the component of fluid with M and N is two empirical coefficient parameters. We consider in here equal to 1. So if we consider Newtonian fluid and M is set to mu0. So here M fixed to mu0 and quantity of N is selected. Then we move this on boundary conditions, which are considered heat, and then initial conditions also. So here we consider steady state flow, and with these conditions. And here we move to numerical methods. So here we consider or we use Finite difference method and characteristic method both for discretization or special discretization, and for time discretization we use fourth order range quota scheme. So here I present the principle of method of characteristics, which is available for this type of system or for a parabolic system. Then here I present the principle of French-Kita method or fourth French-Kita method. Then here we move to application and results. So in this table, we present installation data or data of the problem with tank height, internal pipe diameter, the length of pipe, high viscosity of oil used here, Poisson's 2, and the modules of copper. And then here we move to application with curve. So here we present pressure time history at also my point and at valve of pipe. So these two figures correspond to the pressure heads. It shows significantly that pressure decay and energy dissipation. So here we present also pressure time history at valve of pipe for different values of length of pipes. Here we consider L equal 36 meter, then here equal to 3016, and here 3060 meter. So we can conclude that long transmission pipelines, usually large in diameter and the flow rate, cause negative pressure, which can cause column separation and cavitation. So these results indicate that using equipment when the pumps fail alone does not have the appropriate efficiency in eliminating the dangers in this transmission pipelines. And here we present pressure distribution long pipes in function of time. So with these boundary conditions, the maximum of pressures do not vary much along the pipe. So these observations illustrate that the proposed boundary expression not only improves the ability of the water hammer model to replicate the pressure damping patterns at the valve, but also improves the prediction of the pressure distribution along the pipe over time. So to conclude, this study made it possible to model transit laminar pseudo-plastic fluid flow in a pipe with a couplet of finite differences and range kita and characteristic numerical scheme. So more so, it has clearly shown how the flow of fluids is affected by some of the flow parameters such as fluid viscosity, pipe length. This numerical code can easily be used alongside the excited codes to predict water hammer in the laminar transit viscoplastic flow in pipes. And thank you for your attention.